we're going to be going over fundamental trigonometric identities. Now, we're going to say that they are fundamental because we're only going to be covering the first group, and then we are going to be able to derive more based on this group of identities. We're going to use the identities to change their form to show that things have the same value and they're true. So two expressions that may not look the same are going to be equal to each other, and all these identities are going to be based on sine, cosine, tangent, cosecant, secant, and cotangent. The basic ones that we know already from the unit circle are sine, cosine, cosecant, secant, cotangent, and tangent. And we know that using the Pythagorean theorem, we have x squared plus y squared is equal to c squared. And you're going to see that that's going to be useful for a few of these identities. We can see the pattern right here where sine is y over r, but cosecant is r over y. So the only thing that you're going to be doing is flipping that fraction, or you're going to be looking at the reciprocal. The reciprocal identities are going to be in fraction form. So we have sine u is equal to 1 over cosecant u. Then we know that cosine u is 1 over secant u. Tangent u is going to be 1 over cotangent u. And then it's very similar to cosecant, secant, and cotangent. So cosecant is 1 over sine u, secant 1 over cosine u, and cotangent 1 over tangent u. For these problems, we're using u. You can use x because it's just going to be a placeholder for your radians or your degrees. Oftentimes, you're going to see that they use theta instead, which is a Greek letter. But the main idea is if you were to multiply sine u times cosecant, that's going to give you 1. The reciprocal means that whenever you multiply a number by its reciprocal, an expression by its reciprocal, it's always going to give you 1. The previous 6 were known as the reciprocal identities. These ones are going to be the quotient identities, and the one that they're telling us here is tan u is going to be equal to sine u over cosine u, and cotangent u is going to be equal to cosine u over sine u. This is possible because we have x over y and y over x in our unit circle. That's how we're getting these values. Let's look at the first example. So we are going to rewrite this using the reciprocal identities. So we're going to know everything. We're going to use everything that we already know. And the first thing that we're going to be working with is going to be with the numerator. So the numerator here is cosecant. So we know that cosecant is going to be 1 over sine x. And then you're going to be dividing this by 1 over cosine x. Now, whenever you're dividing by a fraction, again, you can use different methods. I prefer using this method, this to combine and this to combine. So we're going to end up with cosine x over sine x. And we know that cosine x over sine x is going to be equal to cotangent x. So that's going to be your answer. So this is the simplest form. Another way that you can do this is going to be 1 over sine x. And if you use keep, change, flip, you're going to keep that fraction, change the sign to multiplication, and then flip the second fraction. And you multiply 1 times cosine x, which is going to be cosine x. And then you're going to do the same thing with the bottom, sine x. And that still gives you cotangent x. So either method works. Let's look at example 2. So we're going to use the different identities to rewrite this. And yes, we're going to use reciprocal identities, but we also need to use your quotient identities. So we're going to rewrite this as sine x over cosine x. And then this is going to be divided by 1 over cosine x. So this is going to give us sine x times cosine x over cosine x. In this case, you're able to cancel the whole expression, and this is going to give you sine x. So that's going to be your answer. If we were to change this and use cotangent, we would have gotten 1 over cotangent divided by 1 over cosine. But the issue here is that we have different terms. And because we have different terms, we're going to end up with cosine x divided by cotangent x, and then now you will have to put it back into sine and cosine terms, and that will give you cosine x over cosine x sine x. This cancels, but using the other properties, we end up with sine x over 1. So in this case, it's just going to be more work to get to the same answer. So the easiest thing that we can do is use this tangent, put it in terms of sine and cosine, and you put the other one in terms of sine and cosine, and it makes it easier. So we always want to make sure that we're trying to keep everything in the same terms. So if you're dealing with secant and only secant, deal with secants only. But if you have sines and cosines, you need to start changing those things up. For this problem, you're not using x, you're actually using the Greek letter theta. So make sure that you keep your correct variable. So we're going to put cosine theta divided by sine theta, and then this is going to be multiplied times 1 over cosine theta. You can cross cancel, so this one and this one cancel, and you're left with 1 over sine theta, which is the same thing as cosecant theta. So that's going to be our answer, cosecant theta. For problem number 4, now you have two variables. You have alpha and you have beta. So you're going to rewrite this as cosine alpha over sine alpha times sine beta over cosine beta. So this is just going to give you cosine alpha times sine beta over sine alpha times cosine beta. You're not able to simplify this more because you have cosine alpha and cosine beta, so they have two different variables, so we're not going to do anything there. They cannot cancel each other out. Same thing with sine beta divided by sine alpha. That's just going to stay there. Now, in this case, this expanded form is actually longer than our original one, which is okay because the expression is to rewrite. So we are rewriting this expression right here. from this problem, you're able to derive the rest of the identities. The first thing that you could do is divide everything by sine square u. Now, sine square u divided by sine square u is going to give you 1. Cosine square u divided by sine square u is going to give you cotangent square u equal to cosecant square u. And you're able to do the same thing with cosine. So if we had sine square u plus cosine square u, and that's going to be equal to 1. So when we divide this by cosine square u, and cosine square u, we are going to end up with tangent square u plus 1 is equal to secant square u. So these are two identities that you need to know for sure, but you also are able to manipulate the sine and cosine by leaving one of them by itself. So if we have sine square u plus cosine square u, and that's equal to 1, and we subtract cosine square u, you end up with sine square u is equal to 1 minus cosine square u. So you're able to manipulate all these different formulas to try to come up with a new one, and this is all coming just from the basic Pythagorean theorem and applying it to identities function. If you wanted to be a little more creative and you want to say, well, cotangent square u is equal to cosecant square u minus 1, that will be correct, because if you subtract 1 from this side and 1 from this side, you get cotangent square u is equal to cosecant square u minus 1. So this is just trying to come up with different formulas starting from our original sine square u plus cosine square u equals 1. These are the main Pythagorean theorem identities that you need to remember, and then you're able to manipulate things. Again, we can rewrite the second one as tangent square u is equal to secant square u minus 1, because the only thing you do there is subtract 1 on both sides. You can also rewrite that third one as cotangent square u is equal to cosecant square u minus 1. So those are just the same identities that we already have, that we already figure out how to derive them, but I'm just subtracting 1 from both sides and you get a different looking identity. We have discussed that cosine and sine are related because you're able to just do a transformation with sine or cosine to make sure that one graph fits into the other. And that's why we have pi over 2 minus u is going to be equal to cosine u, right? So if we are shifting this pi over 2, we are going to get a function that we already know, because it's going to be a cycle. This cycle is going to start repeating. So even though they look slightly different, you're able to use these properties for others. And this is part of the manipulation that we need. We have even and odd identities, because if you have a negative inside the parentheses in sine, that's the same thing as taking out the negative sign and you put it outside, but you're just going to have sine of that number. So sine of pi over 2, we know that that's 1. But if it was negative, that's going to be negative 1 because the whole expression will turn negative. Now, for cosine, that doesn't happen. The cosine of a negative number is the same thing as cosine of the same number, but in positive form. So it doesn't matter what number you put, the negative cosine of 45 is the same thing as cosine 45. If you wanted to put cosine of negative 120, that's the same thing as cosine of 120. And the same thing applies to secant. So anything that only deals with cosine, anytime that you have a negative, we don't care about that negative. But if you have something with sine, and keep in mind that tangent and cotangent have a sign, then if you have a negative term, you can just find the cotangent of u at a specific location and just make that negative. For this one, we're going to try to condense this into the simplest form. So we're going to use some of the identities as well. So we have sine x cosine square x minus sine x. So we can see that we have a sine x in common. So I'm going to take that out and I'm going to be leaving cosine square x minus 1. From the Pythagorean identities, we have sine square plus cosine square x is equal to 1. So we are able to subtract cosines from both sides. And we end up with sine square x is equal to 1 minus cosine square x. The signs on this side and the sign on this side are different. To change the sign of everything, we're going to just divide by 1, and that gives you negative sine square x is equal to negative 1 plus cosine square x. So we know that this and this are equivalent. So I'm going to rewrite this as sine x negative sine square x. So this is going to give us negative sine cube x. What we need to do in this case is we need to verify that the left side and the right side are exactly the same. Now, we can see that the left side looks very, very heavy compared to the right side. It's the properties of rational expressions. So we need to make sure that we have common denominators. So the first thing that I'm going to do right here is multiply this side by 1 plus cosine x. And you're going to do the same thing on this side, 1 plus cosine x. And then you're going to multiply the other side by sine x, sine x. That's going to give you sine square x plus cosine x plus cosine square x, and this is all going to be divided by sine 1 plus cosine. And we multiply just to get common denominators. Now, you can see that we have different expressions right here, and we want to try to cancel things out. So we are going to change how they look. Because we want everything in terms of cosecant, we need to make sure that we need to cancel everything here so you end up with 1 over sine x. And to do that, we're going to go back to the properties of sine and cosine. So we know that sine square is going to be equal to 1 minus cosine square x. And then we also have a cosine x plus cosine square x. And we're going to have sine x 1 plus cosine x. We have a negative cosine, and that negative cosine cancels with this positive cosine, which is great. Now, we're left with only cosine 1 plus cosine x over sine x 1 plus cosine x. This cancels, and you're left with, and I'm going to put it up here, 1 over sine x, and that's equal to cosecant.